subject to market dynamics. If it can't be reconfigured into an economically self-sustaining system, then it doesn't belong in the picture. So just for some perspective, in 2011, 2.1% of over 1,100 grants by private foundations in the United States accounted for over 46% of their giving, their annual giving to the arts. And these are wealthy collectors and wealthy philanthropists, but their motivations include personal goals, advertising, media exposure. I mean, these drive funding decisions among many corporate and individual philanthropists. But there's a danger because such market pressures can also narrow the cultural experience by favoring the most popular or the most successful art forms, commercially successful art forms, thereby jeopardizing cultural preservation as a whole. So in America, we have a kind of plutocratic philosophy of American culture. It's almost diametrically opposed to the traditions of large public cultural funding found in most of Europe's social democracies and other countries. Unlike their counterparts in other parts of the world, American artists are also expected to be successful entrepreneurs. Can you pull that chair a little bit out of the corners of me a little bit? Get up the other way. Well, that's good. So the United States government funding for the arts is vanishingly small. Federal arts funding amounts to 0.28% of the government's non-military budget. Right now, the arts funding, the principal arts agency, National NEA, has remained static at about $146 million annually, or about 41 cents per American taxpayer. And I should note that most of these funds go to arts organizations, nonprofits, 401, what are they called? Anyway, nonprofits that, and not to individual artists.
And how is the difference with other countries?
I'm getting to that.
Oh, okay.
So, in the U.S., we spend about $7 billion a year from the National Science Foundation budget, and versus $146 million for the National Endowment for the Arts. That's like 2 cents on the dollar. It's a really small subsidy. But the German national cultural budget is $1.63 billion, or about $20 per equivalent of $20 US per German taxpayer. The French Ministry of Culture budget amounted to the equivalent of $10 billion last year. Japanese Agency for Cultural Affairs 2015 budget was equivalent to $863 million, so $0.8 billion, or about $6.73 per capita. Australia spends a whopping amount of $311 per Australian national for cultural spending. Their entire expenditures for arts and culture is about equal to the U.S. National Science Foundation budget. And there aren't that many people living in Australia. The UK spent $76, the equivalent of 76 US dollars per capita for art and culture in 2014. So, in the United States, funding may tend to correlate with more with statistics or voter demographics than with any underlying presumption that government should support the arts. According to the National Endowment for the Arts, some 2 million professional artists make up only 1.4% of the U.S. labor force. So here's artist occupations, about 1 in 1,000 working Americans claim to be professional fine artists. So here's like people who these are U.S. artists who graduate college degrees on the left, and 39% of U.S. artists have no college degree whatsoever. This is the largest percentage. Many have degrees in social sciences, STEM, education, business, and communications, and only 15% in fine arts. And that's contrast really interesting to what artists who graduate with college degrees actually do. 16% are educators, 17% are office workers in sales, 14% are evidently unemployed, service workers, etc. And only 10% of them are artists. And this is really fascinating, since the college degree in the United States is rather costly. On the average, an art degree in the United States costs about $120,000 on average. That's not MIT or Harvard. And people who invest this money have incredibly low prospects for earning a living as artists. So 12% of all U.S. artists jobs in 2013 were secondary employment, meaning they had other jobs. 21% of these hold jobs as teachers, school teachers. So, while many artists have accepted the need to work in more stable fields and pursue their art in off hours, which is difficult, you have to admit, all artists have to face a choice about whether or not they want to value their passion over the chance to earn a decent paycheck. You have to think about what's at stake here. As tough as it is on artists, the alternative is much worse, and that is a world without art. Sapere vedere, right? What that is? It's Da Vinci's motto, this great theme, knowing how to see. We turn our attention to extinct species such as woolly mammoths and Neanderthals. But there's another profoundly tragic extinction that no one seems to see coming. And that is, in order to build a world where it is impossible to pursue the arts, you have to simultaneously crush the human spirit. It's one and the same. It's collateral damage. There needs to be some kind of natural preserve, because the mental health of society as a whole is at stake. BioArt is contend with many of the same economic forces all others artists contend with. Many hold academic positions in art departments at colleges and universities that provide income and tend to facilitate access to the scientific community. But I know very few artists anywhere in the world with primary occupations that are formally embedded in the operations of scientific laboratories. This is from the recently published art review of BioArt. George Church, myself, and 3 others published in Trends in Biotechnology. And I hate to read text off slides, so I'll give you a chance to read the text on the left, on the right. Okay, time's up. So, you're an artist going out to seek your fortune. Like me, we're searching for immortality and limitless wealth. I want to find the Philosopher's Stone. Right? I want to be able to turn base materials into gold. It's the most the alchemical method known as the Magnum Opus, or the great work, is purported to be the protocol for producing the Philosopher's Stone. It's been philosopher's stone's been variously described as sometimes said to be a common substance, found everywhere but unrecognized and underappreciated. The quest for this stone provided a body of knowledge that ultimately led to the sciences of chemistry, metallurgy, pharmacology. Alchemists suggested that the stone's descriptions are all metaphorical, that it's called a stone, but it's not a stone. It's called a stone, but it's not because it's like a stone. The appearance of the stone was expressed as geometry in some of the early alchemical allegorical illustrations. This one published in 1617 by the alchemist Michael Mayer. It was called Squaring the Circle. And I quote from him, "Make of a man and a woman a circle, then a quadrangle, and out of this a triangle. Make again a circle, and you will have the stone of the wise. Thus is made the stone which thou canst not discover unless you through diligence learn to understand this geometrical teaching." Okay, nowadays we have better understanding of the nuclear processes that lead to the formation of stable elements from unstable precursors. Unstable lead isotopes actually tend to decay into mercury or thallium or bismuth and not into gold. You'd be much more likely to eventually get platinum instead of gold. This is an alchemist, Gebir ibn Hayyan from Iran, 6th century, who systematized alchemy, and he brought the empirical method, the experimental method to alchemy. He believed that all metals were based on mercury and mixed in different proportions and different purities with sulfur. If these were perfect proportions and perfect mix, then they would form pure gold. That was his idea. But for the moment, let's entertain the notion that we can ignore physical law and that it's somehow technically possible to transform chemical elements into one another by magically rearranging the atomic nucleus. So we can start with lead-204, which has an atomic number of 82. It's 82 electrons, protons and electrons, and 125 neutrons. Let's see. Note that lead-204 makes up only 1.4% of all lead in the world, so we have to first figure out some way to magically enrich or de-enrich more common isotopes of lead. One problem is that even in cosmological terms, gold is very rare. It is not created in the fusion furnaces of normal stars, where it's assumed that the heaviest elements that can created is iron. Cosmological origin of heavier elements like gold must be extremely energetic nuclear reactions that only occur in very high mass stars. Current understandings of stellar nucleosynthesis suggest that most heavy elements are produced only in supernovas, extreme supernovas, and possibly in neutron star collisions, which is what that's supposed to be. So, another problem is that lead and gold don't have the same number of same ratio of protons and neutrons, so that lead simply can't be rearranged into gold. You end up with extra neutrons no matter how you do it. Okay, so let's say we use our magical abilities to turn lead-204 into a stable gold isotope, gold 197, with 79 protons and an atomic mass of 196.97. That leaves 3 protons and 7 neutrons that will conveniently assume get turned into lithium-7, which has a relative atomic mass of 6.94. It's interesting that the name for 7-Up comes from lithium-7. It was originally a lithiated soda. Soda was like recommended for hangovers.
Spelling orders.
Yeah.
It works. I would try.
So, this is great. We've magically converted a kilogram of lead into gold and lithium, but there would be a change in relative atomic mass of 0.06. In percentages of original weight, this is about 0.3 of a gram. And this would have to be converted directly into energy. So, how much energy is this? We can use this famous equation and we can figure out that 0.3 of a gram of lead converted directly into energy equals about half the energy output of the little boy nuclear bomb, 3 times the fuel capacity of an Airbus A380 ignited simultaneously all at once, 245,670 gallons of jet fuel, or it's 7 times, it's like twice the kinetic energy of the International Space Station should it crash into something at full speed and impact with the stationary object at Mach 45 or at 34,272 miles an hour. So, Rumpelstiltskin, if he was somehow managing to convert straw into gold, he'd have to be blowing up the world at the same time. Naiman, weiß das, ich Rumpelstiltskin heißt. Boom! Tough crop. Some ancient and medieval alchemical texts leave clues to the physical appearance of the Philosopher's Stone, specifically the red stone. It's often said to be orange, saccharine colored, or red when ground into a powder. This is my new Philosopher's Stone. It's a marine sponge called Catia aurantia. It has an internal structure made of glass. These are the glass spicules that make up its endoskeleton. And it does this with a special protein. We know this, well, you have to, so in this image on the right, you can see a tiny little strand in the inside of the glass spicule, and that is the silicatine. It's like you get like 50 micron filament of this protein, and it surrounds itself with 30 microns something about 2 times 30 microns of glass. I'm wrong about that. The filament is, the actual protein filament is 2 microns. So yeah, and then it coats itself with glass to 50 microns. And here you can see the cable-like structures extending from the center of the bisected sponge. And so what we do is dissolve the sponge in acid. And we end up just remaining with these glass. You dissolve the whole thing with HCl, hydrofluoric acid, and it dissolves the glass too. And what you end up is with the protein. And the protein, it turns out, has homology with cathepsin L, which is a peptide, a serine protease. It's peptide hydrolysis. So the steps before gathering the silica, the glass from seawater, it actually polymerizes silicic acid, the most abundant form of soluble seawater, soluble silica in seawater. But so it has to be in solution first. But it's silicatine, this gene for the sponges, is 73% biochemical similarity with this protein that we have, this certain proteins. Yeah, after we isolate the filaments, this is what they look like. And you'll note that these strands are, here are these strands that are, individual strands that are coated with silica that looks like frost, like it's been snowing. Silicic acid. But silicatine is a promiscuous enzyme, so if you starve the media for silica, instead give it some heavy metal, why the protein tries to chelate that metal instead. So there are 3 catalytic amino acids in this, on the surface of this protein, serine, histidine, and aspartame. And site-directed mutagenesis replaced these amino acids with alanine, and it killed all of the reaction with silica. So these amino acids are critical. And with my late colleague Tara Giannoulis, we gave these genes to E. coli, to coat E. coli with a number of different metals. And, we made a bacterial radio, which was exhibited at Ars Electronica. This guy, Lou Bowser, who was at Imperial College for a while, I don't know where he is now. I don't think he's any longer at Imperial. But we met him when he was still out in California. And his thesis was optimizing these biomineralizing enzymes, so over 20 biomineralizing enzymes that were specialized to gold, platinum, and semiconductors like titanium dioxide. But he'd done all this in vitro and never in vivo, so this guy who's standing behind me over here, Ido Bachelet, and myself and Tara, who you just saw, did the first experiments with E. coli.
Is that radio? Did you say some
Pardon?
RFID? Is that
Pardon?
the radio, the bacterial radio?
Yes, that's capacitors and inductors and semiconductor parts of the radio circuit that we then integrated into the radio circuit. So Ido Bachelet's brainchild was bacterial circuits. And I started growing cocoons while I was working on silicatine bacteria. We had a postdoc in lab who was growing silkworms, and he had originally thought to use techniques in synthetic biology to make new fibers for art and science, but then we found out that it takes so long to modify silkworms, the egg-to-egg cycle. His name was Sriram Kasuri. He decided, Joe, I'm just giving you all my silkworm eggs because I don't have time to do this while I'm doing my postdoc. So I went to visit the Transgenic Silkworm Research Laboratory at the National Institute of Agrosciences in Tsukuba, Japan. It's their science city. And met with Hideki Suzuki. And we used transposase expression vector. We used a vector based on an insect virus called baculovirus. And so this on the left is the anatomy of silk protein as it comes out of the silkworm. The silk protein, the principal silk protein is fibrin, which is in the center, and it's surrounded with a kind of gum that we had to remove in order to biomineralize. That comes up later. This is the expression vector we used. And there's the native gene. So we used this expression vector to replace the repetitive in the gene with the sequence, with the silkatine gene. And then these were micro-injected into silk moth eggs. And then these were marked with GFP markers, so we tell which ones were successful when they hatched into silkworms. Now, normally silkworms take 1 year egg-to-egg cycle. There are some, however, wild mutants that are non-diaposal, and the egg-to-egg cycle is only 4 months or so. Nevertheless, it took about 3.5 years to establish 2 stable strains. And so last spring, Hideki came to see me and brought some of our first biomodified silks, our first transgenic silks, which we immediately metallized with silver with my former colleague Mike Sismore and gold. So in the middle, you see the degumming solution, which is you have to remove the gum from the silk protein with a strong detergent, sodium lauryl sulfate, and calcium carbonate, strongly alkaline. So this solution gets, you cook the silk at like 80 degrees C for an hour or 2, and then you rinse it with ultra pure water, and then treat it with EDTA to remove anything that the silk is already, that the silkatine is already bound to, and it's tripped from the silkworm to Boston, and then we treated it with these metal solutions. This is poor Yi, my benchmate, who was making sure I wasn't blowing up the world, and from Holstiltskin. Likewise, Jeff Duval and Seth Shipman, my benchmates. And around this time, Mariko Kasoya, who Casio, arrived from Japan and worked with me at lab for several months while we produced the first silks. I had met her at workshops in Tokyo at Gadai University. We were coding DNA. She loves trees. She learns how to fly. She's also amazing because these filaments, the silk filaments, which we have to separate, are only 8 to 12 microns thick, and I can't see them. I mean, she's going, see? Like, look here. And I'm going, no, I can't see. Who's going to tell the emperor he has no clothes? So we separate silk fibers, which were spun into these threads, and then we degum them with degumming solution, cook them at 80 degrees C, use EDTA, ethylene, guanine, tetraacetic acid, which is the same stuff you use to take rust stains off your kitchen sink.
And so use it.
Yeah, we use it. It's a common reagent in biology labs. So we used gold chloride in solution, and this silkatine structurally integrated, separated and structurally integrated gold molecules into the silk fiber. And so we took this, see what was going on, we took this to the environmental scanning electron microscope at V's Institute in Cambridge. These are what the gold metallized silk looked like in an optical microscope.
You try other metal that's not gold? Like,
Oh yes, we did platinum, cobalt, but I'm getting to that. So my colleague James Weaver at the V's Institute in Cambridge, you can see these little particles of gold attached to the silk in these low magnification SEM images, but higher magnification we found we were getting 2 different forms of crystal structure. One resembling the normal silkatine chelation of silica, but another really strange and unexpected, this flat hexagonal, triangular crystals, which you can see on the left here, that structurally integrated with the silk itself. So there's a non-metallized control and a metallized control, and another metallized control. So the control fibers actually do seem to pick up metals. But the transgenic fibers do it so much better. You can see the difference. And then we did X-ray spectra showing the presence of gold in our samples, and these are some of the gold metallized silks. There's some platinum metallized silks, which we did with the chloroplatinic acid solution, which is platinum dissolved in aqua regia, a mixture of hydrochloric and nitric acid. And I used cadmium too. I was interested in cadmium because of Fukushima. So when Fukushima melted down, there were silver control rods in the reactor, and they vaporized to become metastable silver 110, which after 250 something days decays into cadmium 110, which is now currently one of the big pollutants in the prefecture around Fukushima. So I didn't think anybody was going to let me metallize with radionuclides, but now I'm engaged in projects with the MIT nuclear reactor and nuclear reactor laboratory. And we will be mineralizing with some radionuclides and creating perhaps some of the most toxic, horribly poisonous textiles ever created. But see that chelators, that if you get lead poisoning or mercury poisoning, you're given these chemicals like EDTA internally, and they're fatal themselves because they suck all heavy metals from your system, and you need some heavy metals. And so silk is compatible with human tissue and human body. And I have these dreams of hanging giant mesh screens in the ocean, submarine installations in front of Fukushima to help remediate this distribution of materials, which are still pouring out of Fukushima even as I speak. So, yes, the most poisonous, dangerous, horribly toxic textiles ever created. I want them to be beautiful. They could never be worn by a human being. They could only be installed behind leaded glass in special chambers in the museum. But they'll be exquisitely beautiful, like Sleeping Beauty's apple. Okay, so while I'm on Fantastic Wealth, I made friends with a bank teller in a local bank, and which will remain anonymous. And they have these money counting machines, and after hundreds of thousands of dollars get counted in these money counting machines, that's Bank of Anonymous, bank teller. This is the money counting machine. A layer of dust collects in the bottom of this machine, which routinely has to be cleared out. And this is the dust for money. Yes, this is the dust for money. So, first we just embedded it in a PBS buffer. We're doing metagenomics on these materials. But there's a movie right there. You can see both of these movies. See right there in the middle? I'll back it up when I do it again. This one too. You can see steps from one way. What happened here? I'm going to reopen this because I just had this picture. Here he is. So Wei and Jonathan Shyman, that's Jonathan Shyman. He likes money. He's my colleague. And Stephen met him the other day. What's in your wallet? So we decided we want to know what's in our wallet. John and Wei they're doing metagenomics of the fecal samples of various athletes. They're trying to establish the metagenomics that are special to athletics. And so they're running 16S PCR, which is sort of the most basic form of metagenomics and the most basic metagenomics technique on poop. And so we were going poop, 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 and put money at the end of the. And Mariko, she didn't know she was pipetting poop until I didn't tell her until after. But so, this is our first metagenomic data on the money dust. We got taxonomic references, but we found all kinds of stuff like inflammatory bowel syndrome, vaginosis. We found parasitic fungi. We even found AIDS. So, of this, money is 64 in this band chart right here. And everything that's in red is unknown, can't be cultured, but we can use deep sequencing to establish identities of some of these and identities of all of the small percentages on top, which amount to thousands. And with another colleague, Michael Napolitano, we used this very cool, we fed the data, our metagenomics data, into this cool program to let us determine all different things. So we found staph, strep, we found Clostridium, the organisms involved in gangrene, we found
Means better to use a credit card.
well, I don't know. Credit cards get handled by everybody, and they run through machines like the money counting machines. So, I don't know the advantage of Bitcoin, except you gotta have the keyboard, and you know how dirty keyboards are. But so we found all these organisms: Clostridium, Protobacteria, Archaea. This guy, this duck, is one sick duck, for sure. So, money. I decided to design a $0 bill you pay artists with. And these are all the people who helped me through these various projects: Hideki, Tara, Hito, Sri, Mike Sismore, Seth, Jeff, Boyi, Jonathan Shyman, Wei, Michael Connor, Jim Weaver, Alicia Murchie, who's our former sustainability officer at Harvard Medical School, new research building, and she gave up science, went to the Florida Keys to become a beach bum, but then she came back last summer and stayed with me a month and worked with me in lab on the money dust. It was pretty amazing. Then there's the bank teller who will remain anonymous. Joshua, now in Israel, helped me establish the biological compatibility of silks. George Church Lab and Bees Institute, of course.
It's okay, it's just me.
It's you, huh?
It's
Yeah,
them.
that's
It's okay.
So I thought that your group is interested in synthetic biology for wearables, and so I thought that these wearables that these silks you might find interesting.
Yeah.
I have a new batch of silkworms right now with an even more silkatine integrated into their genomes. Pictures of our new batch Hideki sent me a week or two ago. They are cute little fellas. They're especially good for dessert.
Is your new
Our new batch.
batch of
Pardon?
You imagine brown, so,
Pardon?
Silk runs, yeah.
and so long.
The generic market. Regular silk runs.
And what's the new project with this one?
Well, I'm still interested in bioremediation and of the nuclear, because this Tsukuba, Japan is not that far from Fukushima. And there are children, and I mean, I was in Japan for a few months, and everybody was going, Joe, you have to do something about Fukushima. And I went like, what do you think? I'm a magic infant. But this may be helpful. I may be able to make these silks into cartridges, which could be inserted into groundwater, into wells, into groundwater tables, and then retrieved. It wouldn't call for putting poisonous chemicals into the environment like would conventional ventilators. And then there's the problem of the marine contamination, which I think would be really interesting. But again, these would be producing extremely toxic materials.
So I was kind of working more in, like in the toxic area, or
Well, I have only had limited quantities of silk to run my experiments on. Actually, I have some in my pocket. Well, damn. No, I have some in. But I want to make some, rumble silkscreen materials. So. Golden silk.
golden silk? Is the golden silk?
And this one is a semiconductor. This is for my crystal radio sets. This works like the crystal in the crystal radio set.
That's the one that you use for making the radio, the
This one.
semiconductor. Oh, but the golden one should work.
Golden one wouldn't work for making crystal radio because gold isn't a semiconductor.
Oh.
You need a semiconductor.
But if you metallize with a semiconductor, it should work.
Then I can.
Yeah, that's
That's the idea. But you can make you can weave these fabrics in any number of resonant circuits, not just crystal radios. You can weave them into lasers and motion detectors, and you could create any number of circuits with these kind of materials, which you could then weave into fabric. So you could look to figure out how to build a loom to make inductive carpets.
Well, recently I read a paper about silk that they do that in the skin, and they deposit this in the skin. Silk and also cover with also another, I don't remember which semiconductor, but it's like it goes through the skin. And it's some researchers from Tufts University. Maybe you are working the same project.
With rooftops.
Yeah, Tufts.
With cabins, like
Yeah, I think it's not.
lots of the biopetrol is I used to do mountain as well.
I didn't met him, but I knew that they were doing that in skin, and they were trying to make these sensors using silk, and they use this reabsorption method for making silk in skin to create this.
Everybody gave me my gold back, right?
Go on, go take a look. Okay.
So
Okay.
I'm interested in how this
Yeah.
material worked to weave this silk into the ocean and how to collect this.
Well, weave it first into large nets and then install it in the question.
But what
I would use industrial looms to do it, just like do this on a large scale.
right, but I thought that it would need some very specific conditions so that gold is attached to it.
Well, you wouldn't need to attach gold to it if you were trying to pick up radionuclides. You would just,
Right, but the conditions are different, right? If you are putting them into the ocean, it's not like
no, it will pick up whatever's there.
okay,
Como Victoria's Secret, que se llama Women's Secret,
metal.
y en realidad tienen 800 tiendas en toda
So you don't need any.
Entonces, quiero que hablemos, porque estoy proporcionando
Special temperature or they're just trying to get everything.
Perfecto,
Like all commercial silk, before it's sent to the loom, is all degummed anyway in 80 degrees C. So that would just go on normally, and everything else happens at room
Claro,
temperature.
pero de todas formas, pero digo, you are your